promotion. Docking your pay.
Dang it.
You're supposed to be doing. See what happens when you don't do?
I know.
Capital overlords. So mad capitalist overlords.
That's right. That's right. We need to toil in the sugar mines. Our ant overlords. That's a Simpsons reference. I know a lot of Simpsons by heart. It's like a key part of who I am. And it's embarrassing. I like meet with these colleagues, you know, who, like you go to someone in English and they know, like Michael Bust. Like he just knows everything and remembers directly everything. And I'm like, did you see that? He's quoting like Virgil, you know, like, oh, in the Aeneid it said, blah, 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 and he'll say it beautifully. And I go, did you see that Simpsons episode?
So, even after the first 9 seasons, what most of the fans?
Yeah, I haven't seen like the last like 12 or so.
But you stayed on for
I stayed on for a long, long time. Yeah, yeah. I'll have to check and see when I dropped out. But one of the greatest gifts I ever got in grad school was I was dating this person and her brother gave me a Simpsons tape, a VHS of just a bunch of Simpsons, and oh man, I wore that thing down. Just so funny. Okay, Diana, I just gave you something, right? Okay, cool. I don't know if that happened or I remembered it. Like, you know, I was envisioning that happening. So, a new homework. The final homework will be coming, but I am writing some of these problems myself. I actually want to create some things that aren't in the book. And so tomorrow or Friday, I will have that to you, but it's going to be more creative than just giving you a list of problems out of the book, and I kind of want to have some like, let's investigate some things here and really, really dig in. So, coming soon. And then I'll have your last ones back on Monday. So I apologize for the delay that we had. What are we talking about? We're talking about derivatives, and I wanted to, this kept coming into my mind, that this was the definition we used. This is the definition our book uses for the derivative. And I just wanted to point out that this is probably not the definition you learned in calculus. You probably learned this version. So let's just take a look. Limit as h goes to 0, right? There was an h in it. And you took f of, so this one's at c. So this would look like this, and then just over h. But notice that's really the same thing. And if you look at the pictures, and I didn't draw this picture, but what is a derivative? Well, we take a point c on the function, and we look at the value of the function there, and it has to be defined there. We talked about that on Monday, because we have continuity after we know we have differentiability. So it's kind of a prerequisite for it. If you don't have continuity, you definitely don't have differentiability. And then in this one, we move to some point x. Now, that x could be the left or the right, it doesn't matter. And we find the value of f there. Those are pretty shitty lines. There we go. A little better, feel better about it. So we take these 2 points, and essentially, we're just looking at the slope. So the change in height, which is f of x minus f of c over the change in input, x minus c. And so you can see here that this is just the slope of the secant line. Right here. So this slope equals, and we take the limit as these 2 points coalesce. And at that moment, when they coalesce, we have tangency. Up till then, this is just a secant line. And the minute when they come together, you've got perfect 1-point touch between the line and the curve. So you could actually transform one of these into the other. All you'd have to do here is notice that, let's see, this is, don't write this down yet, because now I'm just kind of like I didn't think this through totally clearly, so if x equals c plus h, then h is equal to x minus c. And so as h goes to 0, that's the same thing as this going to 0, which means x is going to c, right? So that's the same thing. So that's how we can get this, and then this just becomes x, and h, notice that h is x minus c. So you can just make these substitutions easily. The limit's the semi-tricky part, but everything else is really straightforward. Cool, so that was the first thing. And then today I wanted to, since you probably didn't pay properly for these things when you took Calc 1. Your teacher was like, here's the product rule. Enjoy. Here's the quotient rule. Here's the chain rule. You love these, just you don't want to know. It's mostly what I tell my Calc 1 students. You don't want to know. But I know you want to know. Why would you be here if you didn't want to know? So let's prove a couple of basic things. First off, I'm kind of curious if you've ever seen the proof for this, and yeah, n can be anything. Do you know how to prove that? To find that, to like generate you know the answer is the power rule. Let's bring the n in front, n minus 1. Let's take a look. So if x is my variable, so like this thing right here, this is f prime at c. So I have to bring another variable in here, or just rewrite it like, well, this at, how about we say this, x equals c. That'll make life a little bit better. So we go to the definition, and either one is going to be just fine. I don't think there's a terrible advantage between the two, or one over the other. So this is going to be x to the n minus c to the n over x minus c, and that looks pretty straightforward. Oops, how about a limit, buddy? There we go. Yes. What can we do? If it was x squared minus c squared, we'd be all over it, right? Difference of two squares. Hell, if it was x cubed minus c cubed, we might be all over it. I don't know how all over it you would be. Let's just take a look. So let's just look at the pattern here. And some of you are going to go teach this stuff, so I think it's really important to see it. So this is difference of two squares. That's cake. This one is x minus c times x squared plus xc plus c squared. Vaguely familiar? Yeah? What do you think the general factorization is? So let's see. So lim x goes to c. This top thing, you can definitely pull an x minus c out. What think ye about those parentheses? Pretty bad. Pretty bad.
The thing where it's like the x to the n minus 1, and then you need the pyramid thing that I can't think of.
Yeah, oh no, we actually don't need that. So that's, I like that you're thinking of the,
Fibonacci.
yeah, the Fibonacci, but the, who's trying, Pascal's triangle. It's actually a little more straightforward than that. Notice the pattern here. We started with 1 degree less of the power, which makes sense, but then the powers decrement by 1 on this first term and increment by 1 on the other term. So the c's start out c to the 0, c to the first, c squared, x to the x squared, x to the first, x to the 0. So that's really the rhythm here. So this is going to be x n minus 2 times c. We just need the total powers to be n minus 1. And then eventually we'll just end up with a good old pure c term by the time the x's die out. I got really stressed in calc the other day because I talked about killing something or it died. You know how I always say that with zeros and stuff. And then I started thinking, shit, I hope that doesn't trigger people. Because like nowadays, like in the last 5 years, I'm always worried about triggering someone with something. And it was mostly honors that did that to me. you know, because somebody was always triggered in honors. Very sensitive group of folks in general. But, and then I was like, oh, I'm sorry, I hope that, maybe I shouldn't say that. And then I just pushed it to the limit, and I started I was like, let's choke it out. I started talking about choking out a variable. It's the end of the semester. So, yay, boom. Can you finish that up? I'm gonna grab this for Anna. There you are, friend. Oops, sorry, paper cut. Is that a mate or a matcha latte?
Yeah,
Matcha
my
latte,
mom
yeah.
said it is somewhere.
Nice. You mean eraser? I've only been reported to the president once of the university.
Are you for real?
What's that?
Really?
Yeah, it was because it was a long time ago. It was like my second year here, I think. And I was teaching linear algebra, and there was a student in there who came up to me and was like, hey, I'm gonna quit school and become, I don't know what he was gonna go do something. I was like, cool, well, I wish you well, you know? Sounds like you know what you wanna do, so good luck. His mom wrote a letter to the president because I didn't try to stop him from quitting school.
That's the dumbest reason.
It's so fucking stupid. Yeah, each of these becomes a C, right? So we've got a whole chain. How many of these are there? Correct. Thank you, sir. Because when we cubed it, there was 3. When we squared it, there was 2. And that's not enough of a reason, but it makes sense that we could extrapolate to n here. So that's just n c to the n minus 1. Congrats. You now can use the power rule. Right? You got that. Let's take a look at some other. Because these are where they get kind of cool. And then the chain rule is really, really quite intense. But we're going to do it anyway. So the product rule, you're going to like this because it's got an old friend in it that you've seen like maybe every 2 weeks in here. And I bet this is you will walk away from this class knowing this trick, if nothing else. So we want to find the derivative of f of x times g of x at x equals c. Everything's good. These are differentiable where we need them to be. So everybody's happy. So all functions are content. Maybe that might be just content with being differentiated. That's the longest way to say they are differentiable. I'm super punchy, so that's okay. I'm just gonna roll with it. So this is going to be limit as x goes to c, f x g of x minus f at c, g at c over x minus c. Now you know where we gotta go with this, right? We know the answer is gonna be f prime times g plus f times g prime. Bless you.
Thank you.
We gotta fit them in there somehow, so check out the trick. We insert 0, like this. So this first one I'm gonna say minus f at c g of x plus f at c g of x minus f at c g of c for x minus c. Right, every other week we're doing that, right? It seems like it, I feel like it. So, this looks like it makes things worse, but now we can break this apart into 2 pieces, and I'm gonna do multi-steps here. So notice that if I just look at this first fraction, there's a common f of x and a g of x in those first 2. So this first one is g of x times f of x minus f of c over x minus c plus, now here I can pull an f of c out. And I'm left with g of x minus g of c over x minus c. And we're done, right? We're done because this is the definition of the derivative of f, and this is the derivative of g because of the limit. So this goes to f prime at c, this goes to g prime at c, and I got me, and then this goes to g of c as well, right? Because x is being replaced by c. So, it's f and c, g prime and c. So, now we got that. That's way more work than the quotient rule. Quotient rule actually is going to fall back to this rule. We're going to do that too, because I want you to see that trick. It's a beautiful, beautiful trick, actually. So let's now find the dx of f of x over g of x. Everybody's happy, nobody's zero when we're dividing. All things are good. So, first thing I'm going to do is rename that function. I'm going to let big F be that quotient. Oh, sorry, Keila.
No, you're good.
Okay.
Thank you.
Let me let you get caught up real quick. Just rest for a second. Let everybody get caught up. Look at this. It's like have to be entertained constantly. Take your own advice, old dude. So check it out. Now I can turn that into a product rule by just multiplying through by g of x. So in other words, f of x is big F, little g. Can you finish this? Apply the product rule and then find the derivative of capital F. And then solve for that. So step here, apply. I want to let you do it because it's cool. Apply product rule. Solve for that dude. And enjoy. That's beautiful. Right back. Yeah, cool. It's kind of cool. It's amazing how well that trick works. Looks like you got it, Noah. Got it to work. Cool. Anybody else feel like they're getting somewhere with this? We all started this way, I hope. If not, probably just stop writing, because I don't know what else to do beyond this as my starting place. Remember, this is the thing I'm solving for. So at this point now, I can just replace capital F with its definition. Oh, maybe I should solve for it first. That just, yeah. Solve for this guy first, just to like, it doesn't matter. It would have been okay what I just did, but. So you're gonna subtract that from both sides. And we're already starting to get something that looks quotient rule-ish. Divide by that G. And now replace that. And I think that just is a slightly more elegant way to do it. So that's just f of x over g of x times g prime of x over g of x. Clear out the fractions, top and bottom by g of x. Gets you your old friend. Oh, wait, hold on. Something.
You forgot this f prime.
Yes, awesome, cool, that would have been scary. So this is f prime g minus f g prime over good old squared denominator. Cool, so now you can prove, these are two things that you could probably easily remember how to do and then show someone you're tutoring. Oh, let me show you how the quotient rule comes about, right? It's like, on top of it. This one is not the kind of thing you probably just carry in your back pocket. That's the chain rule, which is probably the most useful of all the rules, I think. Certainly, this is when things get fun in calculus. That's what I'm actually talking about. No, I already talked about that one. Anyway, sorry, just rambling up here to myself. F of g of x, I want that derivative. That's composition. And what we're going to assume is the following, that g maps from A into the reals. So let's just draw a little bit of a picture here. So I've got g mapping from some set A into the reals, and I want f to feed off of the output from g. So we could call this g of A right here. That is a subset of the reals. And then f is going to be defined on that. So what would they do in the book is they say take a set B that contains this. Does that make sense? When I wrote there, it's kind of weird. So g of, here about this. So just say it like that. G of A is a subset of B, and then f maps from B. Its domain is something that contains the range of G to R. So, in other words, we've got G doing this, creating the G of A thing, and then we're hopping all that into F and getting its inevitable output. So we start from the definition. There is this one actually does require some serious finesse. I think that's the word they use in the book. I think I mentioned that on Monday about something else, the continuity proof. But this is going to be, let's get a point. I like having it at C, otherwise we have to introduce a Y and then things start looking a little scary. And this is f of g of x minus f of g of c. Oh, no. Yes. Yeah, that's the whole thing. Yep. And I think I'm already off track. So that's what we want. We want that limit, but we can't start right there with that limit. Is it okay if I erase here? Nobody's writing on the left. Okay, cool. Thank you. Maybe I should go. Yeah, I want my little picture up there. 1 minute. So what we're actually going to do is start with, I got to cheat. I was trying, man. I went through this like 4 times this morning, and I was hoping I wouldn't have to use my notes. But since G is differentiable, F is differentiable on G of A, that's one of the hypotheses I didn't write up terribly clearly. G prime at F of C, sorry, and my notes are asked backwards. I put F and G wrong, so apologies for that. So F at G of C. So in other words, we've got this point C here. We run it through G and get this point G of C, and then we're plugging that into F. So put F prime at G of C. Now I think I'm going here. That's what I need to prime myself up. Is going to be the limit as some point Y approaches the place where we're evaluating. So this is G of C. And then up here, I'm going to have F prime at Y minus F prime at G of C over Y minus G of C.
Why is F prime?
Thanks.
Okay.
Thanks, Noah.
Cool.
Okay, it's not, because, yeah, good call. Thank you, sir. So check this out. This looks a little bit weird, but here, just imagine that this is the point C from that original definition. I mean, actually, let me write it out. So we could do here limit as, Z approaches something else. We've got some point here, and there's just a general representation of that. So it's literally just that, but we're using G of C as our point. So it looks tricky, but it's just this right here. And we're going to call this expression here, this quotient, d of y. So let d of y, kind of think of it as derivative if you want, is going to be this ratio. And we are going to treat this d as a function, and we want it to be continuous. So we want d to be continuous on G of A. That set that we're taking is all its possible inputs. So right now it's not, right? Because right now it's not continuous. It's not even defined when y equals G of C. So we're just going to define it at the place where it has trouble. So define G of D of G of C. What would be a good definition for it? Well, let's look at what we're actually doing here. We're taking the derivative of f and evaluating a G of C. And literally that's right here, but we could have discerned that by moving backwards. So this limit is this, and continuity means your value equals your limit at that point. So to have this thing be continuous means we must define it to be f prime of G of C. That has to be the way. All right, so now let's take on, we'll get rid of this. We'll put it back up if we need it. So now this function's all pretty chill. It's all nice and happy. I'm going to multiply both sides by y minus g. So notice that this says d of y times y minus g at c equals f at y minus f at g of c. We're almost done. That's the trick, like getting a d in there and then making that note about continuity. And from here, we really are almost done. We're almost done. So think about what is this y? What is y? Well, y is a point in G of A. Y is a point in G of A. So y equals f of a g of t for some t in A. We don't know what, but we know that must be the case just by its definition. So I'm going to replace that expression up there, y in that expression up there with g of t. So star, that's a lot of so's, and change it up, thus. Star becomes, I'll use a hence next if we need one, d of g of t times g of t minus g at c equals f at g of t minus f at g of c. Now we really are almost done. We're going to divide through by t minus c. So now, divide. Let me make sure. Wait, hold on. Oh yeah, perfect. Divide through by t minus c, and what we're going to get is, I'm going to divide this product, and this is what my brain was frying on for a minute. So this one's going to get the division. So I'm going to have d at g of t times g of t minus g of c over t minus c. See, now look, a derivative starting to pop out. This is going to be the derivative of g here. The inside part, right? This is the inside part of the composition. And then this is going to equal f at g of t minus f at g of c over t minus c. So look at what we got here. When we let t, let me let you get caught up. Let me pull up a nice lounge chair. Sip my tea. Just, yeah, get caught up. Let me know if there's any questions or corrections. I think I'm okay after Noah set me straight. So think about what's going to happen as t goes to c. As t goes to c, well, first off, we can write this dude back up here. So this thing here, let's just rewrite it first. Finally, unraveling d gives, that's nice, that's a good math word. I've never used that in a proof. To unravel something, that's great. And so d is that ratio right there. So this is actually f at g of t minus f at g of c all over t, all over y minus g of c. But this is f of t, sorry. Wait, g of t, thank you. Yep, cool. G of t. And then this, just everything else just copies. There's some interesting things going on here. Because there's two things that look an awful lot alike, but there's a subtle and important difference. Look at the levels of differentiation here. This one, we're actually differentiating with respect to just t. So this is just a straight up derivative here. So as t goes to c, this just goes to the derivative of the outside part, right? This is just, if you want to write it like this, here, actually, right? You think about the top like this. This is f of g of t minus f of g of c over t minus c. Notice that now it's just treating the composition as our function that we're differentiating. And so this just goes to the derivative. And we can use t here or x. I'm just going to change it to x because that was our original variable. Doesn't really matter. That's just a placeholder of f of g evaluated at x equals c. You see that? See, make sure you see that one is literally just that expression, which must be this when we take the limit. But look at this one here. Here we're not moving the t closer to the c, we're moving the input to the f closer to this input of the f. So notice how this is like up a level from that one. They look a lot the same, but in the end, it's what I'm dividing by that's telling me what's moving closer. So this thing here just goes to f prime, so I'm differentiating the f, but I'm evaluating at g of c. And that's st goes to c. And then this guy right here, this is happy, right? That's just g prime. So times g prime at c, and that's equal to that, and that's the freaking chain rule. That's a lot of work. That's a heavy cost, but it's the last burden I have for you today. At least that burden. Let's get a more refreshing burden. Let's switch packs. Everybody rotate packs. And let me know if there's any questions about that. I kind of wanted to work. Oh no, I think I wanted to, something Noah had mentioned to me. That's right. Let's take a look at a cool example. So here's a question I have for you. For what values of alpha, which is a real number, is f of x equals x to the alpha sine of 1 over x? Let's start off with continuity and then get deeper into it. So step 1, continuous. Question mark. So let's sketch this thing out. And actually, maybe let me pop up Desmos. Should have done this like an hour ago. We'll see. Maybe we'll be in good shape today. But I can talk about it while this is coming up. So when you have something like this, let me just kind of show you a neat way to think about things. And I've got sine of some stuff or cosine of some stuff. This thing here acts as an envelope. And that's the technical word for it. So it's an envelope for that function. And it governs its magnitude, right? Because you know that if I have this governs the magnitude, right? This number out in front. If it's 3, then it's 3 high. But that's a constant thing. So this is a variable envelope as well. So for example, while that's heating up, if I had, e to the negative x sine of, I don't know, just whatever, make some garbage up there, that means that I've got a sine curve, so a good old sine, and we can figure out the details if we wanted, but its magnitude is controlled by e to the negative x, bless you. Bless you. So I've got this envelope acting like this on the thing. And so when I multiply this by this, I'm going to multiply similar values down here, and what that curve ends up looking like is a dampened oscillation. Does that sound reasonable? Yeah. So, and you can do that with any function you want, even if you put another trig function out in front. Things get kind of fun. now I've got a trig function whose envelope is a trig function, and you might see something like this go on. Right? So, got like this other waveform happening here. And yeah, so we've got that happening up there. We know that sine of 1 over x is pathological at 0. Right? Remember that sine of 1 over x, and I think we did talk about this. Notice, just look at this. When x is really big, this is essentially sine of 0. So way out here, it's like 0. And then it comes in and starts oscillating, and that goes faster and faster and faster. And it's not even defined at 0. So maybe we should define it at 0. Let's do that. That's when x is at 0. Let's let it be 0 when x equals 0. That'll make life easier. So we just have a little point right there. And then out here, it's the same thing, but sine is an odd function. So you've got asymptotic behavior out there, and then blah, 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 blah. Pretty crazy looking. My drawing is pretty crazy looking. It adds to the craziness of the whole thing. But let's take a look, get some intuition from Desmos. You know, friends, you're going to be mathematicians, and every mathematician needs a picture of graphs are going to be your friend. And if they're not already, you should be plotting more. You should, because there's a lot of intuition that can come from. So check this out. We're going to do x to the a. Look at how it adds a slider for me, because it's so freaking smart. So it says, oh, there's a slider, great. So we can control A, and then we're going to have sine of 1 over x. Voila. Like so. Ooh, my picture is off, apparently. Yeah. Huh. Oh, okay, I see. So I was thinking sine is an odd function, but then so is x to the first. So an odd times an odd is an even. So there's actual symmetry here. So that when x is negative, this is also negative, and that flips the whole thing. Cool. So see, look at that graph corrected me. I gained some insight just from looking at it. I think it might be clear. Ooh, let's get a smaller step size here so we can actually understand what's happening. So let's say 0.05. And then let's let A go. It seems right that A should be negative, doesn't it? Yeah, it's going to be terrible. Truly. We'll put a negative 1 in here so we can see that mess. And then let's just, I think 3. So going up to x cubed will be plenty. So look at how beautiful Desmos is. And let's go down here. So now I'm taking a 9th root of something, and even though that might be possible for a negative, Desmos is barfing on it. But, ooh, look at that, it's kind of happy. So we're going down, there's the half, and we can actually pull back out. Take a look at that. So that's like a cube root, there's a 5th root of x out in front. And notice that as we approach 0, these, can I make this just go a little bit slower? It's starting to approach the crazy, the pathological version. So at A equals 0, everything's a mess. But as even just a hair above that, we see that this thing is starting to die out. Let's go to the negatives. Oh yeah, look at that, right? So, I mean, you're dividing by 0, right? A couple of times, inside the function and outside the function. So we've got this crazy asymptotic behavior there. So we're not gonna even mess with that. But we are going to try to understand continuity and differentiability of this thing for varying x. So you can see that as soon as x has a positive coefficient, this thing actually starts dying out, right? You can see it dying out like a root function, like when square root. Here, this one you know. Square root looks like a parabola turned on its side, and you can kind of see that there. That's square rootish enough. But you see that good old square root of x function kind of enveloping or enveloping this thing. And then as we move up, you see it doing what actually seems pretty reasonable, just dying out in different ways. That looks like it's dying out really fast. In some ways, you couldn't even tell that those crazy oscillations are going on here, but they are. You just have to dive in deep enough. Let's see if we can get in deep enough. I don't even know if, oh yeah, right there, I can see it, right? You can see the above and below kind of stuff going on, and then if you get in close enough, indiscernible from a normal sine curve. Okay, that was enough intuition. And actually correcting myself, so that was good shit. So continuity. We know that alpha has to be positive. Is that enough? That's the question. Is alpha positive going to do it for us? Oh God, oh, wait, what time is it? Is that?
10:24.
Thank you, okay, got it. I was glad it was quarter till already. So the way to do this would be to take a look at this quantity. We're going to start here, and we want to show that we can make this less than epsilon if x is close enough to 0. That's all we need to do for continuity. So start here. Let's just start here, right? And that's kind of the end. We do this a lot as well. We start at the end and work our way backwards and get a proof together that way. So what would this mean? This would mean, so we need this. This would mean x to the alpha sine of 1 over x. Luckily, we defined f of 0 to be 0. That's cool. And then this is x of alpha. Just remove that 0 so things look a little happier. Can somebody help me here? Boy, that sine of 1 over x is a mess. Makes it really painful. What can we do?
We can put it less than or equal to just x of alpha.
Yeah, exactly, because that's the envelope, right? This sine function is between -1 and 1. So its magnitude is never more than 1. So if we note that this is the case, that this thing here is bounded by absolute value of x to the alpha, because that's the envelope, right? So look, I'm moving everything to the envelope. I could have put an e to the negative x out here, and that would be over here instead. And now it's not too hard to get this thing less than alpha, or less than epsilon. So it ends up, it becomes a proof that x to the alpha is continuous at 0. And that we can handle, and we've done that. Let's actually do that. We're assuming alpha is positive, so that makes life good. Can you actually finish it? Can you tell me what the delta would have to be, please? What is the delta response for a given alpha for x to the alpha? ahead and start if you want. What is differentiability going to require on alpha? That's a bigger so that you get to just go into that. Here, hey, Noah, there's a cave. Get in there and check it out.
Okay.
How's it going? Make sense? Yeah? What do you think alpha is? What do you think about delta response is? Not sure. So, how it works, we want to get it down to a statement just about x. So let me show you. Yeah, right up. So now I'm going to show x cubed is continuous at 0. I would start, I really would need to find the delta response, so the range of x that makes this true. So that means this has to be true. That's kind of, we're kind of at that point over there. So now, think about what the delta response is. It's going to look like this. So I need to find this delta. So when this is true, this is true. Right? So I want that to imply this. So now I just work this into that. So how do I get x isolated over here? What do I need to do to both sides to just get that to there? What operation is that? Yeah, so the cube root, exactly. Yeah. So epsilon to the 1/3 does that. So now this is my delta. Because now if x is less than epsilon to the 1/3, this is true, and then this is true. So you see how that might apply over here. All right. Let's go in here. Yeah, okay, wow, okay, yeah, that's beautiful. It's just so tiny, I couldn't even see it. I'm just so, it's too old. It looks red. That is red. I love it. That's kind of cool. Yeah. So solid. So solid. Feel free to start on differentiability or just do nothing and enjoy the universe. You feel good? Okay, so. Where can I write?
Anywhere.
Anywhere, okay, cool. So this is what I'll show Diana. If I wanted to show that x cubed is continuous at 0. I'm going to look at this. So I want this to be less than some arbitrary epsilon. So I need that. I need to find the range of x around 0 that makes that true. So in other words, we want to find this delta so that when x minus 0 is less than delta, that implies this. So watch how I do this. So now I'll take this. This just means that is true. And so instead, cube root of both sides. If x is less than the cube root of alpha, then this is true. Then this is true for an arbitrary epsilon. So this shows me my delta needs to be epsilon, cube root of epsilon. So now you give me an epsilon, and I say, okay, then if x is no further than this cube root of epsilon from 0, you've got this true. Yeah. Yeah, oh Lord, yeah, that's gonna be painful. So it's actually a lot simpler. So once we get here, like, what do you think we need to have x less than to have that? So thinking through the same thing, what's gonna be over there? And that's gonna be your delta. Does that make sense? You're making it way more, yeah, it's not too bad.
Thank you.
You're welcome. All right, how do we feel about a delta response of cube root of epsilon? Oh, and sorry, sorry, just finished. The alpha root of epsilon. Yeah? Because, so let delta be, this is your response, so that if x minus 0 is less than delta, that tells me that x is less than delta. That tells me that x is less than epsilon to the 1 over alpha. Raise both sides to the alpha. So x to the alpha is less than epsilon, and now I can just insert that 0 in there. Look how I got a proof of continuity. Wunderbar. So this thing is going to be continuous at 0 as long as alpha is 0. And x to the alpha, you know, looks like this. When alpha is 1, it's good old y equals x. When alpha is greater than 1, so here's alpha equals 1. When alpha is greater than 1, it looks like the old parabola. When alpha is less than 1, it looks like square rooty. But either way, it crushes the function to 0, and that's all we needed. We needed to dampen those oscillations, completely kill them as we approach 0. So now what about differentiability? Anybody done anything with this? No? What are you thinking?
I think it has to be greater than 2.
Cool. It's definitely, yeah, it's definitely away from 0. I was thinking 1, but definitely 2 is going to work for sure. So I think that we might be able to extend it just a little bit more. Did anybody else do more work on this? Kayla, you were thinking about
I
it.
started doing it like by the definition of the derivatives
the way to
to
do
see
it.
where we would, like where it needs, what alpha needs to be.
Cool. And you hadn't quite chased
No.
that completely. Yeah. So let's do that. So let's look at now differentiable, which means we need it to be smooth at 0. So let's go to the definition of differentiability. We're going to take a look at f of x minus f of 0 over x minus 0. And we'll worry about the limit after we do it, but this is the quantity that we're interested in. So this is going to be x to the alpha sine of 1 over x minus 0, as we defined it, over x minus 0. Let's put it here. And then I'll get rid of all the x's, and this turns into x to the alpha minus 1. Sine of 1 over x.
Oh, I did chain rule x.
Oh.
Some,
Oh.
yeah, slightly different.
So,
which is why I thought it
so
was-
you assumed it was differentiable at 0.
Yeah.
That's, yeah. Gotta be careful. I think. I'm curious what, I want to do the chain rule in a minute because I want to see what you saw. Very interested in that. But does this make sense? Yeah, and there's, slap that shit on there, right? And so if I want that to be less than epsilon, or no, let's see here. Here we want the limit of this as x goes to 0. That's even easier. This is bounded. This thing here is less than or equal to this, because that's the envelope. So this must be less than or equal to, by the limit order theorem, this must be less than or equal to this. It's certainly greater than or equal to 0 because of the absolute value. And then this, as long as alpha is what? This is going to go to 0. Greater than 1, as long as I have some x there. If this is negative, that's going to blow up to positive infinity. So here we need to have this, need alpha minus 1 to be positive for this limit to just equal 0. And so if alpha is greater than 1, we have differentiability. And I think that it's probably, not being able to intuit that might also just be, you're not familiar enough with these x to a tiny little power above 1. So if I were to ask you to plot this, it's hella close to the diagonal. But it's not, because it will grow. And what you end up with is just the slightest little curve here. And then they both intersect at 1, like that. But you start to get a little bit of curvature out of it as soon as that's a slightly more than one thing. Alrighty. Well, my friends, that seems like a pretty damn good place to start. I don't think we want to start anything in the last minute. I will tell you where we're headed. What we want to do is get to the place in the book, and you could read ahead if you want. I think it's 5.4. We want to talk about a function that is nowhere differentiable. So we're going to build that. The nowhere differentiable function. Now think about what that means. Remember that differentiable is the same thing as smooth. So what we are going to produce is a function where there is no interval at all where it looks like that. There's no smoothness. There's nowhere to rest on this function. Everywhere is rocky. You say, no, wait, get smaller. Surely if we get a little smaller, it'll look like straight. But it won't. Why do I say straight? Because, let's actually, one last thing. So I do have one last thing to tell you. When we say that a function that is differentiable is smooth, what we mean is that it's locally aligned. So differentiable implies smooth, and that implies local linearity. And what I mean by this is as follows. Let's say I've got some function that's super curvy. Woo, sharp, almost cut yourself on it. Pretty dangerous. But it's still like a parabola in some ways. And so what I do is, a derivative is really a magnifying a microscope. Derivatives are microscopes that blow up areas to let you know what it looks like if you zoomed in an infinite amount. So if I blow this up, so blow up, this would look like this. So let's see here. So like, yeah. And then I just keep blowing up that spot. So I blow that up again. And this is, I'm looking through my little microscope, right? Like that. And then I blow it up again. And it's almost indistinguishable from a line. So differentiability means that at the tiniest levels, you look like that. And that's why we can get tangent lines. A tangent line is just a magnifying glass on your curve. So we are going to produce a function that no matter where we zoom in, this doesn't happen. Well, look, here's an example of our favorite non-differentiable example, absolute value of x. So think about this. Absolute value of x look like this, super sharp. At 0, it's not differentiable there because no matter how much I zoom in, that doesn't change. That shit is sharp. Sharp as shit. Forever. You can't get rid of that point. So, but notice that just to the right, it's okay. Just to the left, it's okay. We're going to produce a function that there's nowhere to go.
But it will be continuous?
It will be continuous.
That's weird.
Isn't that weird? Yeah. So we're going to produce one rocky-ass function. That'll probably be the last thing we do. I'm not sure. We'll see. Thank you very much, my friends. Thanks for waiting the extra minute. Thanks for the false ending and still being here with me. Thank you.